Oh, yeah, somebody mind closing the door there. Well, welcome everyone to Ken Chapman's defense. I'm Troy Gilmore. I was Ken's advisor. And as Ken will share, we kind of have a longer history together, and I hope you enjoy some of that background story. One of the people who's online is Francois Virgan. You'll hear his name. And it was in his lab that Ken and I really started working together on some of these topics. Some of the things that I've really benefited personally from working with Ken is truly a lifelong learner. He does a lot of work volunteering on projects, and that's really how we got started. And I really appreciate that kind of generosity that's been he's lived out. And he also is really good at building networks and relationships, which will also come up as part of this project. And so a little bit of background on Ken is that he's vice president of imaging algorithms at Thrive Bioscience right now. He has a BS in business administration from Oregon State University in 1978.
I had hair.
And he had hair, and an MS from University of Texas, El Paso, 1990. And then he started here on his PhD in August of 2019. He's been working full-time and also running me pretty hard on the evenings and weekends as well throughout this whole time period. So I really appreciate, Ken, all the work that you've done. I'm excited for you to share what you have accomplished here at UNL. And one of the things that I'll mention is this booklet, which I'm not sure how many of you on Zoom can see it. I sent a little picture of it to the committee members who are online. But this whole book is the monthly updates that Ken sent his committee every month. So he's now raised the standard for current and future PhDs. And my lab, this is a dissertation of its own. But anyway, that's been a lot of fun to follow. Really appreciate everything. Turn it over to you. Can we make sure we hit the record button? Thanks.
Thank you very much for the really nice introduction, Troy, and thank you everybody here, both online and present, for coming. This is a presentation of the dissertation titled Measurement and Prediction of Stage and Discharge with Ground-Based Imagery in fulfillment of a PhD. My committee members. It's not working. There's a switch on it too. Oh, there's a switch on it. There we go. My committee members are Troy Gilmore, who's the chair. Aaron Middlestead is a committee member and a reader. Mary Harner is an outside member from University of Nebraska Kearney, and she's also a reader. Ruby Oglu is a special member. We're thankful that she was willing to come in here and help us from Texas A&M University Corpus Christi. And Andrew Harms is the final committee member. I'd like to thank them very much for all of the things that they've done for me during this 4 years that I've spent at UNL. So this is my first time in Lincoln, actually, and I just wanted to let you know that I do have some Nebraska bona fides. My grandfather Otis was born in Madison, Nebraska in 1893, and my grandmother Ethel, these got to be good Nebraska names, was born in Lynch, Nebraska in 1898. So I'm just going to start off with a little background on how this whole thing got started. In hydrology and ecology, it's really, really important to be able to measure water level and discharge. And those are used for a plethora of different, I won't go through all of them, water distribution policy, discharge calculation, lots of things are informed by the ability to measure those things properly. I have spent my career, the last 40 years, working on developing imaging algorithms. And so when I came here, we wanted to look at how we could use image processing and evaluate images to extract information that was of interest to hydrologists and ecologists. And there's many uses if that's possible to do that. So what are we talking about when we're talking about images from which you can extract information from that have to do with water? What we do is we just point a camera at a stream or a lake or a body of water and start taking images. They're stored on an SD card in the camera and then retrieved at a later date or passed over the internet or via satellite to a storage server. We do some image processing and we can create, in this example, a hydrograph, the water level over time. To do that accurately, the state of the art right now is that you have to put something that's fairly intrusive into the scene, and that's the thing that we have been working on is these kind of targets that you put in the scene so that you can measure stage as accurately as possible. There's the camera that we're using in one of our studies, and we'll talk about that a little bit later. Some more. So when I first came here, Mary at Kearney and Troy put their heads together and developed a heuristic because there's really, we're kind of in the early stages of using images for water right now. And to do things accurately, you have to do a lot of things to the scene to make it possible to measure things properly. And so they identified that as something called a highly conditioned image. If you have to put something in the scene just so that you can measure things, that's a highly conditioned image. There are also lots of repositories of images by a lot of people that we'll talk about that have very varying levels of conditioning. But the conditioning doesn't have really anything to do. The conditioning wasn't put there to be able to do image measurements. Examples of that would be staff gauges and some images. And if there's a Weir image, that's something that the image processing can use to do image alignment in a time series. Then there are images that have literally no conditioning at all, and there's nothing in the image that's really very helpful for doing image processing. Kind of the holy grail is to get to the point where we can gather important information from unconditioned images. Oh, no. Oh, I got it. Am I the right one?
Maybe just use the keyboard.
Yeah, I'll just start using the keyboard. Okay. So the thing that we know from the work that we had initially done that Troy alluded to with Francois Birgon at North Carolina State University was develop some methods to measure stage in images. And the thing that we found that the less conditioning that there is for an image, the less intrusive the targets are that you put in the image, the fewer things that you have to make those measurements properly. And the idea that we had, that Troy and Mary had, is that they wanted to maintain the precision of measurements that we're doing and see if we could extract meaningful information from images that had less conditioning than what we were currently using. The product down at the bottom is a software product called GRIME, that stands for Gauge Can Remote Image Manager Educational, was where we started. And it did a pretty good job that we'll talk about doing that, but we wanted to move up that curve to use less conditioning and still gather meaningful information. As far as we got in the work that I did, is we did feasibility work on working with semi-conditioned images to see if we could pull information out of those, with the idea that that would lay a foundation to do future work in unconditioned images and still get meaningful information. So we had two main things that we wanted to do. We wanted to evolve the current highly conditioned measurement techniques to make them a little bit less conditioning and easier to use. And we actually installed targets in a good number of places in the Kearney Outdoor Learning Area, south of Kearney High School in Turkey Creek. Mary and her team and Troy installed targets there. There's targets installed at the Goodman's Library. We have a partner with whom we work, have been working for a year or two now, Jessica Wilhelm, who is using these targets for intermittent stream studies at University of Kansas in the Bergen Lab. And so that's the body of images that we'll discuss, that show our work, the research that we did on highly conditioned images. But then we wanted to do something in less conditioned information. And really the main question we actually wanted to ask is there really enough information in the images to measure predict discharge? And those images are the ones that we talked about that are semi-conditioned or unconditioned. There's large repositories literally around the world. Here's a few that I've listed that are in the US, the NSF NEON project, Northern Arizona, University has a big thing, USGS has a big thing, and we work predominantly with a big repository of beautiful images taken by the Platte Basin Time-Lapse Project. So with the idea that we wanted to improve our ability to use those images, a second objective was identified. On most of the studies that we saw that had to do with water and images, the software that was created for that analysis was either single-use one-study software that was good for academic use only, and it really wasn't repeatable in usage. We wanted to build a piece of software that virtually anybody could use, that it was free and open source, and so that was a primary goal. In addition to that, we wanted to do these other things that we've already talked about to increase our ease of use in easy to use in conditioned scenes, and then determine whether the content in semi-conditioned images was useful. So 3 studies were identified, and we'll talk about that. When we first started out, Dr. Burgond asked us if he thought it was, asked Troy and I whether he thought it was possible to measure water level in images, and there was nothing to start with. So what we did is we got a bread pan and a bottle of water, and I had an old piece of software, and we ran that, and I wrote an algorithm. It's not a great algorithm, but it worked really pretty well, and we demonstrated that we thought that we could do it. I'm going to show you a video of this now, and it's got some pretty cheesy music in it, but it talks about a river, and I think it's kind of cool. So I hope you appreciate it as much as I did.
The original story for this production.
Yeah.
Taking the clip on the right screen.
There's lots of links. There we go. So you'll notice that the red line here is following the water level, and we're going to pour some more water in here. We literally did this on a desktop in an evening or two, and we demonstrated ourselves that, yeah, in fact, we can find the water level in an image. And so we thought it was worthwhile to continue that project and try and take it out to someplace that was more useful than a red pen on the desk. This is a very long story. This slide holds a lot of work that was done over the years. To demonstrate that we could actually do this in the real world, Troy built a lab setup that had a pump that pumped water in and out of a tube so the water would go up and down, put a staff gauge beside it, and we did that successfully. We put that same setup out into a stream in Pullen Park on the North Carolina State campus, and that worked really well. We were able to measure water level there too. We built up a bunch of lab tools. This is my son, Christian. You can tell how long we've been working on the project now by looking at him. So that culminated in 3 referee journal articles and a poster. So it's been a very, very successful project. There were some problems with that though. The program that we ended up with, we wanted people to be able to use it, but it was hard to install. You couldn't save and load stuff easily. There's no really good batch tools. And then the algorithms were not as good as we wanted, and it had a bunch of bugs in it. So we identified the first project is to create a grind tube, gauge cam remote image manager educational tube. We had to add the educational part so it would say grind. And so we did. We created that package. It was a very successful effort, and I'm going to describe all of the features of what was actually created. We built a program that is available with a Windows installer on GitHub. Anybody can go down. You can go down and download it right now, install it, and we'll talk about what it does. It has a commercial-friendly, free open source license. So you can see the source code, you can modify the source code, you can use it commercially or do anything you want with it and you're fine. Installs all of the prerequisites. It's just a one click to start the install and go through everything. And it installs both a graphical and a command, user interface and a command line interface. We're going to go through that a little bit to describe why that's important. And one of the big innovations that we had was when it installs some demonstration images that allow you to run the program in a calibration file. So the instant that you run the program, you can train yourself and see if you've got the program installed correctly. In addition to that, there's a website that has a bunch of how-to videos that explain the usage of this program, and it has been adopted for use for research in a number of places that we'll discuss later. So what do you get when you install? You've got all of the standard image browsing tools, so you can click through a folder of images, zoom, pan, look at color, grayscale, load and save images, and even create animations for presentations. We improved the calibration so that after you enter the data that's needed to perform a calibration, you press the button once, it calibrates the image, puts up an overlay, load and save those files. It shows what the error is of the calibration on the calculations. Then from the program, from the GUI, there's a batch run utility, so you can run many images with just one click of the button. They'll start running. It shows the output on the screen. It saves the results into publication quality overlay images so that if you're doing some research, you can do that. It creates a CSV file output, which is literally the hydrographs, so that when you're doing if you're doing a publication, you can use R or Python or whatever tool you want to create hydrographs. And then this last thing is not as apparent, but it's very important. We use best practices, the kind of practice I use in my day job. Had a standard versioning scheme, release notes, documentation for the developer documentation in Doxygen, commonly used libraries, OpenCV, Qt, and Boost, developed it in Linux, and if you can build it on Linux or Windows, and I suppose you could even do Macs if you wanted. We haven't tried that. And the reason that that's important is that we want people to be able to do with this whatever they want to do with it, and to extend it or change it if they've got a better algorithm than us. Finally, we've got a command line interface. It does all of the functionality we talked about before, including calibration, running folders of images, creating overlay images, and so on. And the reason that this is important is because the functionality is encapsulated in a command line program that can be called from batch files. So if you have a whole bunch of images that you've downloaded to run, you can build a batch file to run that, but you can also do process calls to use the tool of your choice. You can use MATLAB, Python, R, C++, Delphi, or any language that you want, as long as it accommodates process calls, and that's important for developers. So the next project, after we had the software up and running and it ran very nicely, we wanted to improve how it worked, as we've discussed previously. So we wanted to do some target improvement for RIME 2 better than the bow tie target. To do that, we needed a test setup to test what we're going to test. And I'll talk about the octagon target that was designed to fulfill this part of the research. But Dr. Harner, Jamila Bajalan, and Troy set up and maintained this setup here, which we'll talk about in more detail in just a second, in Turkey Creek, south of Kearney High School, by a fallen tree. And we installed there both a traditional pressure-based water level sensor, 2 targets, and a camera. So the reason we installed the traditional sensor is that we needed ground truth. But Aaron, several times in the time when we worked with him, is always worried about variability. And we know that there's variability in the ability of this HOBO sensor to be able to measure properly. And there's a bunch of different things that can go wrong with that sensor. And I won't go through them all, but the bottom one on the list is one that come up and bit us, that you'll see in the hydrographs in a little bit. So with that in mind, we'll go on to talk about the octagon target. The octagon target notice that the width of the octagon target is significantly less than the width of the bow tie target. And that was one of the goals of the project, is to reduce the size of the target so that more of the image could be used for contextual analysis if something went bad. And that turns up its head in a little bit. The target was built so that it would always be out of the water. And we kind of blew it on that one because we had an unexpected high flow that covered our target. So we changed the code a little bit to be able to accommodate that. But the reason we wanted it always out of the water is because it allows us to do a full perspective transform in every single image. So if the camera moves, it doesn't matter. Or if we're taking a picture from two different cameras, it doesn't matter. The calibration captures in every image and it accommodates any motion or any of those kind of things. With the bow tie target, that wasn't possible. All of the bow ties had to be visible for a calibration to be possible. That happened infrequently, so we had to do a special accommodation to calculate whether the target moved by looking at the top two bow ties and then just doing a transform that handled translation. It just diminished the accuracy when a full perspective transform was not possible. Then also very, very importantly, with the bow tie targets, there were 16 independent measures that needed to be made when you install the bow tie target. After the bow tie target is installed, you need to know what the position of the center of each of the bow ties in X horizontally and Z vertically relative to the zero water level identified by the hydrologist. And so that was an onerous task. Sometimes transoms are used. There's different methods used to do that. Those values needed to be entered into a specific, specially formatted file to be used at time of calibration to read that to perform the calibration. With the octagon target, because of the shape of an octagon, all we really need to know is the facet length of that octagon to start the calibration, and then the distance from the bottom of the octagon to the zero water level. Those are just two numbers that we just enter into the GUI and just one click and it calibrates, and it just works very much nicer and reduces the complexity of image calibration in the GUI. And we did really, really well. These numbers might look a little bit big, and we're up in the 4 centimeters land. We're comparing the bow tie versus the octagon is the yellow, and they correlate very well to each other. They're the yellow and the red. The octagon versus the sensor, there's a little bit more error, and the bow tie versus the sensor, there's even more error. And the reason for that error, we're going to take a look at in just a second, and you'll see why the sensor is significantly different than the image-based methods. So here are the hydrographs of the bow tie calibrated measurements relative to the hobo sensor measurements. I'll talk about some aberrations first and describe the image. First of all, when we first looked at the data, we saw this huge flow event. And all we were looking at were the numbers from the scalar sensor, and we kind of didn't believe it. And ironically, that spike happened on Halloween night, and when we found out it was the real deal, we thought it might have been some kids or something. We had no clue. In fact, because we have images and not just scalar values, we could go look at the images, and the flow event did happen. And you saw kind of an image of some of that flow event previously. But there was a plateau that occurred with the hobo sensor data, and we strongly believe that the barometric pressure sensor that was installed, along with a traditional pressure sensor for water level measurement, was installed too low in the tube, so it got covered with water, and there was no way didn't have the ability to adjust the water level based on the water pressure sensor, because barometric pressure sensor, because it was underwater. The third thing that we ran into was that there's a square wave manifested in the bow tie target at the top. And that is because we calibrated this top signal with just one calibration taken from the visible light image. This camera has actually two cameras in it, one with a visible light sensor for day and one with an infrared sensor for night. And they're apart from each other. And because they're apart from each other, they require different calibrations. And if you don't use different calibrations, you can get a square curve. So when we, to fix that, we calculated the measurements for the daytime images with the daytime calibration and the nighttime images with nighttime calibration, and it smoothed this out. So it just matched almost perfectly the hobo sensor until we get to the plateau. Finally, there was some kind of an event happened at this red vertical dashed line that caused there to be an offset in the two measurement levels between the hobo sensor and the bow tie calibration. And in addition to that, there was a small rising spike and falling spike that we weren't sure what it was about. And the reason I'm calling all of these out is we're going to walk through and talk to you about how we were able to back out the information and figure out what went wrong because of the fact that we had images. So let's take look, before we get into that, let's take a look at the octagon results. With the octagon results, you notice we never did have a square curve. We're calibrating in every image, so it builds us a smooth curve, and we follow the hobo sensor curve perfectly until we get, except for the plateau, until we get to this red dashed line again, and you're still manifesting. We've still got a little bit of an offset less than the bow tie, and we still got these spikes here that we don't know why. So to figure out whether we had motion is we found the position of the fiducials in of the octagon and the bow tie fiducials in an image after this event, and then overlay them on an image of the before the event, and you can see that there was camera movement. This demonstrates that in fact the camera moved, and we found the fiducials are in a different place. So for these little spikes that happened here, I'm very sad to say that we were able to evaluate the image, and there was a small amount of biofouling that turned out to be just a little bit stronger than the very faint water line in these two locations. And so the water line search algorithm failed in this case. So let's look at that graph again. We didn't put the bow tie to octagon comparison. They were very good. So when we believe that we would have been a lot better than this if the plateau was missing, and if during that event that happened, when the camera moved, that these numbers would have been significantly smaller because we're comparing them against something that was not optimal measurement from the traditional sensor. And I might note that that line, that vertical line where that event happened, it was at a time when there was camera maintenance done. They cleaned the target to get rid of biofouling. They took the SD card out of the camera, so there was some kind of motion that happened in that sense that probably caused both the offset and the offset. So we think we did really good work, and we're very successful in getting a target. The octagon target actually is better based on the numbers that we found than the bow tie target. It's easier to set up, but there's still issues. There's sensitivities associated with the fact that these targets, because of the perspective transform that we're doing, need to be orthogonal, completely orthogonal to the water. And if they're not, then we have to create a much more complicated calibration, and that's actually much less accurate. And the target needs to be stationary across measurements. Recalibration and camera movement detection doesn't help at all for target movements. It helps only with camera movement. So if there's camera movement, we're good. If target movement, we're not. And then again, as we saw in our experiment, the target must not be obscured by biofouling. So there's a maintenance requirement. You've got to go out and clean that target or pick some better target materials. And there's a big opportunities for future research. I worked fairly extensively with 3D cameras, stereoscopic LiDAR, and projected point grid 3D cameras. There might be an opportunity to do something to improve that there. But also we have some very good ideas on how to build a three-dimensional target that will handle that you can install on non-orthogonal surface. That's for future research. So the final study that one wanted to do now was to really study the information content of semi-conditioned images and see if it was really possible to get information out of them. We wanted to find stage and predict or estimate stage and discharge, and we wanted to see if that was possible. So we had to pick some semi-conditioned images, and Troy suggested that the Platte Basin time-lapse project pictures of the North Platte River state line weir on the Nebraska-Wyoming borders, this is a Google map image here, would be a good candidate for that, because there was a USGS gauging station there that had lots of stage and discharge data. And there we have lots of images taken, very high quality. These images were not captured for scientific purpose, so the camera was not as stable generally as a scientific camera might be, but they're beautiful images and very high resolution and very nicely done. And so we decided to use a repository, 40,000 plus images between 2012 and 2019 to do this study. So the idea was to attempt to extract information from the images. So we needed the place we started was based on my experience. I kind of do this daily for the last 40 years or so, is extract features from images. And so we wanted to extract features and figure out whether they actually informed the stage and discharge within that image. Based on the USGS discharge and stage data that corresponded in time with when the image was taken. So we calculated features, we merged the features with the stage measurements. We'll just talk about stage for now, and then we divided the data into test, training, and test sets. And we created machine learning classifiers based on the training set, and then tried to predict the test sets. And if it wasn't good enough, we calculate some error metrics, reduce the noise, and if it wasn't good enough, then we'd loop back and then throw out some features and get some other features until we found something that we thought predicted things fairly accurately. And we did a good job at that. We think we picked some very, very good features that allowed us to do that. And the features, I'll give you a sense for some of the features that we picked. When you're working with these kind of features, it's not only what the feature is, it's the location of the feature in the image. And so whether you're in manufacturing or in rivers or in cells or anything, you're worried about location in addition to the actual what that you're looking for. So the first thing what we did is when we first looked at these images, Troy said, gee, it seems like that white water says something about how much water is flowing and at what rate it's flowing over the weir. So the shape and size of that white water might be a good feature. And also the water above the weir is flatter than the water below the weir. So maybe the texture of the water has something to do with those, with the stage and discharge. So we calculated those. And in addition to that, there's a bunch of generic features that you can calculate for any area of an image. The color of the image, we used hue, saturation, and value, HSV. So we calculated the mean and sigma of that. There's texture features like Shannon entropy, the edge magnitude, the mean and standard deviation of a Sobel magnitude image for each one of those areas, and use those as features. So I'm going to show you a video of this running, and you'll see the area of the white water bouncing around as the images change over time. Okay. You see this changing here, and these blocks. So there's some images that we couldn't evaluate because they were too dark or for some other reason, but most of them we were able to evaluate properly, and you can see the areas below and above weird areas, and we calculated for the whole image and in that area within the green. How did we do? So after we had a set of features that we thought worked very well, we created artificial gaps in the USGS data. So we had all of this data. We removed the year 2015, just as an example, and then we built classifiers from data before the gap and the data after the gap, and then tried to predict what was in the gap by just using the features from the images, and then calculating features from the images that didn't have where we didn't have data. And in fact, we were able to do a great job at predicting stage and discharge, or estimating stage and discharge at those times of the gaps for 2016 and 2017, and most of 2016 also. But there was an area in 2016 where there was a high flow rate where we failed pretty badly. And after quite a bit of investigation, we realized that the training data from the before and after the 2016 gap manifested no high flow rates at the level that was in 2016. So we felt that if we had high flow data to train with, that we could predict properly. And in fact, that was true. We tested that out by doing a 2016 half year and using high flow data to train each half of the year from its partner. And we were able to predict the half year discharge and stage accurately. Okay, so now we'll go on to conclusions and future research. We absolutely believe that we met our goals. There's a great software package out there that's available for use, and it's being used, and we'll talk about that in just a second. We improved grind 2 methodologies by quite a lot with the octagon target, reducing the size of the target and making setup way easier to do. And we determined that, in fact, there is information in those semi-conditioned images that's worthwhile trying to mine. And we'll talk about that in a subsequent slide. But that work has already started to figure out how to mine data from unconditioned and semi-conditioned images. And in doing all of this, we established relationships and continued relationships with several institutions who are either developing with us or using our software. North Carolina State University, I continue to work with Dr. Francois Virgon. I'm on the committee of one of his master's students, and we're looking at measuring flow of water out of culverts. We were really glad to work with Ruby at Texas A&M Corpus Christi. She helped us with our initial collaboration with the TESM system that we'll talk about in just a second. And she uses some of the data, and we expect to continue working with her. Thanks to my brother-in-law, Lauro Pedraza, we have been able to establish a relation with a very important university system in Mexico, the ITESM university system. Later in June, Dr. Hildardo Sanchez and 2 of his students will be delivering a paper at a conference in Sinaloa based on the semi-conditioned image data that we created. Troy and I are co-authors on that paper, and we're very grateful to be working with them. We continue to work with some of the students in their classes and hope to expand that relationship. We're very thankful for Jessica Wilhelm at University of Kansas. She is using the grind 2 software and the grind 2 octagon target. She's also used the bow tie target in some of her intermittent range studies in the University of Kansas. Idaho Power did a prototype study in remote Hells Canyon to measure water level, and was very successful with that. And then a very important collaboration that's going on right now, United States Geological Survey has provided UNL a grant to help them with their use of images and extracting information from images, both deterministically and with machine learning. So we're very thankful to be working with all of those. So moving on forward on the research, the first thing that's the most obvious is to continue to improve the grind 2 product and build a target that will allow us to do non-orthogonal surfaces, because if you want to install something on a bridge abutment that's not vertical, then you have to do a special apparatus. But probably the more important thing is after we finished the semi-conditioned image study, Troy recruited a student that I have worked with for 16 or 17 years now, who's an expert in machine learning, artificial intelligence, 3D imaging, and image processing. And he's well down the development path in the development of a product that we're calling, or a tool we're calling the Grime AI tool, that's being produced in the spirit of it's called Grime AI. It was being developed in the spirit of the Grime 2 tool, to be open source, free, and it does a lot of things with semi-conditioned images. It gives you data access to these big, automatic data access to these big data repositories, pulls down whatever data is available, not just images, but nitrogen data or climate data or whatever is available, and merges that data with the images, performs image triage and segmentation, and it's taking us well down the path toward getting better at handling semi-conditioned and highly conditioned images. So, or I mean unconditioned images. So finally, I want to do some acknowledgements. I'm going to go through this very fast, but in no way do I want to diminish how grateful I am to my committee and how kind you've been to me, and I just don't have words for how much I've enjoyed this PhD program. I want to thank my bosses, the CEO Tom Farr, and the Chief Science Officer Alan Blanchard were kind enough to provide me the time to go do this, let me leave to go do class, and supported me every step of the way. Two of the scientists that work under me, Frank Evans and Mark Singer, were very helpful. We had lots of colleagues and collaborators. My son, Christian, has been extremely helpful. He's a co-author on both of the papers that one's published, one's in review. He helped with this presentation and just a million things. He helps with the math a lot. Then John Stransel, the student who is working on the Grime AI product. We collaborate very closely. Andrew Brown, Francois, we stay in close touch with him. I'm very grateful to be working with him. Jamila deserves a special prize because she went out into Turkey Creek in the cold and the snow and maintained those targets. And we're very grateful for her, the work she did. Jessica Wilhelm, who's working at University of Kansas, we really enjoyed that and are continuing to collaborate with her. She's been tremendous in that collaboration. I have people, my cousin Tricia helped me do the proofreading on this thing because I'm an engineer. And then the Platte Basin Time Lapse Project provided all of those, all of the images. I want to also say thank you to John Carroll and Matt Jokel, because I know they had to make special provisions for someone that's past retirement age to come here remotely. And I see Martha back there. She was one of those people that helped me out. One of the seminar class instructors. I'm in awe of the classes that I took and the goodness of the professors in making special provisions for somebody that was taking classes remotely. And then Kelsey walked me through a bunch of administrative tasks that I never would have been able to happen if that hadn't happened. We're very excited about ITESM. My brother-in-law, Laura Pedraza, and his old classmate from ITESM, Mario de la Fuente, at the ITESM Guadalajara campus, and Professor Gildardo Sanchez. We have great hope for expanding that collaboration. And I want to give special thanks to my family. My wife and my kids put up with a lot. Me talking, I'm sure Troy's family did too, talking to Troy on weekends and on holidays and strange hours in the night. My parents are gone, but they very, very much would be grateful to know that I'm doing this. And then special thanks also to my Mexican family, who have also been very, very supportive. With that, we're ready to move on to the public questions part of this thing. And I'll put up an image. We had tons and tons of spectacular wildlife images from this project, from the North Carolina State days until now. The top three here are, there's a bison and deer. These were provided by Jessica at University of Kansas Bergen Lab. And then these other three images were provided by Mary at the Kearney Outdoor Learning Center, the raccoon and the heron. With that, we're open for questions. And anyone who wants to ask a question on the chat, Troy will read those questions out loud.
Any questions in the room?
Yeah.
So, like you mentioned that biofouling could affect where the water level was. Did you also like see if like the color of the water could also impact it? Like did it seem like a clean or a sediment choked stream?
Yeah. So the thing, the long story on this is there was continuous improvement on that algorithm. And one of the things that I do in my day job is to try and find out if that line that's in the image is really a line of interest. And sometimes the line that you're interested in is not the one that's the most evident algorithmically in the image. We put the water, the bow tie target into Hell's Canyon in these remote locations, and the water was so pristine that we couldn't hardly see anything. Right, it just looked like it went all the way down to the bottom, and so it was a struggle. And so I did a lot of things to do. I did a lot of you can do things like taking a series of images in a row and then aligning them, and that allows you to kind of magnify the contrast at the boundary. We had going in our favor that on the water side of the bottom side of the image, the water was going to be continuously dark, usually even in the clear water sense at University of Idaho. And so we could use the fact that if there was white space past the biofouling, so start looking from the bottom up as opposed to the top down. And there's a lot of other techniques that we use. We use a lot of amortization of, we evaluate 5 or 6 columns at a time, and then do what we did was we found a bunch of points across the line, and then did a ransack fit on those points to throw out outliers. And so there's a bunch of techniques that are in there to handle that problem. But it's a really good question because we fought that one for what, 14 years now.
Great, thank
Yes.
There's a question in the chat. You'll be really surprised. Francois has a question.
Oh, I'm very surprised.
Did you use manual/visual readings in assessing the polygon octagon prime 2 performance?
Manual readings.
Manual/visual.
Oh, yeah. So did we look at the image to actually see where they were relative to the staff gauge, that kind of thing? In fact, we did not do that very much because of the correspondence of all the lines. The times that we did manual inspection of the images is when we ran into anomalies. The plateau in the sensor reading caused us to want to go look at those images. The movement of the camera caused us to want to look at those images. That little spike, we looked at those images. But other than that, we did no manual inspection or manual measurement. Martha.
Really nice presentation.
Thank you very much.
My question is related to application.
Yep.
Do you foresee some sort of application here for, the general public, producers?
So that's a really, really good question. And one of the big things that we tried to do in the rebuilding of the Grime 2 product from Grime was to make it really easily usable so that it could be used in the context. We're right below Kearney High School, right? And so we see big learning opportunities there to be able to, for the students to use. It's easy enough for a high school or junior high school student to use these tools and transmit those images and build hydrographs and that kind of thing. The area where I think that the applications are going to be really explode, though, is with the Grime AI product going forward that John Stranzel and Troy are heading up. And what that does is if you have a set of images that you want to ask questions about, but you don't know what those questions are or what might be available, performing the image segmentation on unconditioned images does automatic binning of things. So you have masks on the image that say these things belong together and these things belong together. And so to give you a sense for what kind of application that might be applicable to the general public, suppose somebody is interested in seeing when ducks come onto their pond, right? So they start taking a series of images on the pond, and with this Brime AI product, we're able to segment a duck. And we don't know that it's a duck, but we know that it's different than the other stuff that's there, and then make a definition of that duck so that we can either go out and investigate a whole bunch of images, or as we take images, flag that and send you a text to say, hey, there's a duck. And in fact, that's what I do in my day job predominantly, is we're looking at viruses and finding out when medication or when viruses are killing cells. And so literally we do that exact same process that we're hoping to put into Brime AI. When cells are dying, we send a text or an email to the scientist that's working on those cells so that they can go into the lab and see the things they need to see or perform maintenance. Did that answer the question?
Yeah. Well, I was thinking about,
Yeah.
can you tell me what's going on in the Republican River if I want to do down there, right?
Yeah, yeah.
The depth and.
Yeah, absolutely. And we can do that, I think, now, I mean, that's essentially, we can transmit those numbers now. It's just a hydrograph. But you can also look at the USGS data. It's already there. So, yeah.
Yeah, very nice.
Thank you.
Yeah. So you say one of the limitations you're not able to calibrate the target. Right?
Yes.
So have you thought of like maybe georeferencing those targets?
Doing what now?
Georeferencing?
Georeferencing.
Yeah.
We have talked about that. Okay. John Stransel has done a lot of that. And he said about a year ago, says, Ken, have you thought of georeferencing? And that's the extent to which I thought about it. But that's a really good idea, but I've got to finish my dissertation. But it is a very good idea, and it's something that should be evaluated whether we can do that. But it's good. We think our gut feel is that we need a much higher resolution camera to do the georeferencing to get the precision of measurement that we want.
Do you remember the features that ended up being significant in the semi-conditioned image models?
Yeah, it's been a while back, but the thing that we got some surprises, as you would expect that you always do. Of course, the whitewater boundary area worked fairly well, and just the area and the texture differences between the upstream and downstream boxes. You remember the blue and yellow boxes. In addition to that, we were very surprised that the whole image color features added a lot of information to our ability to measure the stage and discharge. They alone didn't do anything, but combined with the whitewater features, it helped a ton. So, yeah, it's a good question.
Ruby asked a question.
Okay.
She was asking, when using daytime versus IR images or nighttime images, what was the quote time of day unquote when the algorithmic transition was made from visible to IR?
So that was inherent to the camera. So we didn't. There's actually metadata in the images that's put in the images by the camera that tells us which one it came from. And in the case of that's what we used in the case of the bow tie target, but we didn't care with the octagon target. Lo and behold, it met our purposes because it did perform the calibration of whichever image it was in, and it just worked fine without knowing that. That was a really good question, actually, too.
Any other questions in the room?
Yeah, thank you, Martha.
Yeah. There is another question in the chat from Lauro. Ken, besides taking a deserved rest and good time in Mexico, by the way, we are already waiting for you to celebrate. What plan do you have for the near future, and what would be the new milestone you guys have planned on UNL and Monterey Tech or ETESM partnership?
Okay, so Lauro is my brother-in-law, who's kind of Etessum gadfly and knows everybody down there. And it's hard to overestimate the importance of that university system in Mexico. It's just, they do produce a lot of engineers. It was modeled after MIT, actually. Our plans are to continue working closely with Hildardo. They have some students that are very interested in ecological and hydrological questions, but also have deep skills in machine learning and artificial intelligence. There's a pool of very, very skilled artificial intelligence people on the Guadalajara campus of Etessum, with whom we're fairly closely associated now with Hildardo Sanchez and some of the other people that are down there. And we hope to continue working on that, predominantly getting them involved in Grime AI as much as they will.
I'll just add to that, that Saturday we'll be attending the capstone courses for for those students that have done projects related to imagery, and they spun up, for instance, the data portal for FOLA. And I'm really hoping that we can continue to share project ideas with them and work together with those students who are undergrads and would be great grad students up here.
Yeah. So, thank you for the question, Laura.
Thank you so much, Troy and Ken, and congratulations once again.
Thank you.
John Stranzel has one for you. Since images are currently taken every 15 minutes or so, not a very fast frame rate, what are your thoughts on hyperspectral imaging?
He would ask that question. So just to give you some context, that John and I worked in a pharmaceutical application where we were using Raman spectroscopy and pill shape and size to determine what pills were in a bottle, to find out whether it's drugs and that kind of thing. So John has much deeper knowledge than I do about hyperspectral imaging, but my expectation is that in many contexts, the hyperspectral imaging will give us knowledge of the chemistry of the things that we're looking at. Whether it be erosion studies like Aaron likes to do, or if there's enough information in the water that we might be able to do that. But John can answer that question better than I can.
No other questions in the room? Well, there's no more questions in the chat, so maybe we can take a break. Thank you, everybody.
Thank you, everybody. I really appreciate you guys coming.
About 10, 12 minutes, 10 minutes. Yeah.
Yeah, very good.
Maybe after 2 years. Yeah, we need to have you guys over, but yeah, Monday I'll see you. Yeah, I want to talk to you. No, I'm. Yeah, thank you. All right, see you later. All right. Good evening.
Thanks so much.
Yeah, thank you a lot for coming. Appreciate it. Glad you're staying at UNL. You never give up.
Nice job, Ken.
It's a lot different than what I planned.
My goodness.
Some of it's based on the truth too.
You guys got in last night?
Yeah, we got in, we went and picked up Christian in Omaha yesterday. And then immediately went to Abe's for hamburger.
It's a good place. Which one did you get?
I got the the top left, the standard thing and with the grilled onions on it. It's the best hamburger I have.
I know, I always get the spicy one.
Fireside?
Yeah.
Yeah, they spent too much time in Latin America.
I had that spicy.
Yeah.
I had the fireside, and then at one time they had a limited edition that had was pepper or something.
Oh.
And it was just like a hint, I mean, just a hint, and it's still like lit, and the girl's still,
Yeah.
Sam Phoebe still make fun of me.
One time I grilled a jalapeno and I ate it and the girls said it was like a cartoon. My face, just they could see the red.